Good morning, everyone. In this presentation, we are going to study different types of AC bridges used for measuring inductance, capacitance, and frequency accurately. AC bridges work on the same principle as the Wheatstone bridge. When the bridge is balanced, no current flows through the detector, and the unknown electrical quantity can be calculated using balance equations. Now let us discuss the Maxwell inductance bridge. The Maxwell inductance bridge is used to measure an unknown inductance by comparing it with a known standard self-inductance. In this bridge circuit, four arms are connected in a bridge form. One arm contains the unknown inductance L along with the resistance R1. Another arm contains a standard variable inductance L2 connected in series with resistance R2. The remaining two arms consist of non-inductive resistors R3 and R4. An AC supply is connected across one pair of opposite junctions and a null detector or galvanometer is connected across the another pair. When the bridge reaches balance condition, no current flows through the detector. At this condition, the impedance ratio of one pair of arms equals the impedance ratio of the other pair. So we obtain I1 into R1 plus j omega R1 plus j omega L1 is equal to I2 into R2 plus j omega L2 and the I1 R3 equal to I2 R4. From these equations, separating real and imaginary parts gives the balance conditions R1 R4 equal to R2 R3 and L1 R4 equal to L2 R3. Therefore, L1 by L2 equal to R3 by R4. Now let us discuss the Maxwell inductance capacitance bridge. In this bridge arrangement, the value of unknown inductance is measured by comparing it with a standard capacitor instead of a standard inductor. This method is more practical because standard capacitors are easily available and highly accurate. The bridge consists of four arms. One arm contains the unknown inductance L1 along with its resistance R1. Two arms contain non-inductive resistors R2 and R3. The fourth arm contains a standard capacitor K connected in parallel with the resistance R4. An AC supply is connected across one diagonal of the bridge and a null detector is connected across the other diagonal. When the bridge reaches balance condition, no current flows through the detector. At balance, the impedance ratio satisfies Z1 by Z2 equal to Z2 by Z4, where Z1 equal to R1 plus J omega L1, Z2 equal to R2, Z3 equal to R3. Z4 is the impedance of the parallel combination of resistor R4 and capacitor C. The impedance of this parallel branch is Z4 equal to R4 by 1 plus J omega C into R4. Now let us understand how the unknown inductance is calculated in the Maxwell inductance capacitance bridge. When the bridge reaches balance condition, no current flows through the detector. At this point, the product of impedances of opposite arms equals to becomes equal. So the balance condition is Z1 is Z4 equal to Z3 Z2. Here Z1 equal to R1 plus J omega L1 represent the unknown coil. Z2 equal to R2, Z3 equal to R3, Z4 is the impedance of the parallel combination of the resistance R4 and the capacitor C. Substituting these impedance values into the balance equation and simplifying, we obtain the R1 into R4 plus J omega L1 R4 equal to R2 R3 plus J omega C R2 R3 R4. Now by Equating the real parts and imaginary parts separately, we get two important equations from the real part. R1 equal to R2 R3 by R4. From in the imaginary part, L1 equal to R2 R3 C. The advantages of the Maxwell's bridge, the balance equation is independent of frequency. It is useful for measurement of wide range of inductance at power and radio frequency. The scale of resistance can be calibrated to read inductance directly. And then the disadvantages, it cannot be used for measurement of high Q values. It cannot be used for measurement of very low Q values because of balance coverage problem. Now let us discuss the Anderson bridge. The Anderson bridge is actually a modified form of the Maxwell Lane bridge. It is mainly used to measure the self-inductance of a coil accurately using a standard capacitor. In this bridge, the unknown inductance L along with resistance R1 is placed in one arm. Two arms contains non-inductive resistors R2 and R3. Another arm contains resistance R4. A standard capacitor C is connected through an additional branch along with a small resistance R. An AC supply is applied across the bridge and a detector is connected between points B and D. The important feature of the Anderson bridge is the extra branch containing the capacitor, which improves measurement accuracy. Using Kirchhoff's voltage law, loop equations are written for different loops of the circuit. At balanced condition, no current flows through the detector. Therefore, currents in the corresponding arms becomes equal. So I1 equal to I2 and IC equal to IR. Also, according to current law at the junction, the incoming current equals the outgoing current. These relationships allow us to derive the balance equation of the bridge. The Anderson bridge provides high accuracy, precise inductance measurement, use of fixed standard capacitor instead of variable components. However, the circuit analysis is slightly more complex compared to the Maxwell bridge. Hence, the Anderson bridge is widely used for accurate measurement of inductance, especially in laboratory applications. In this slide, mathematical analysis is carried out using Kirchhoff's law for different loops of the bridge. Applying loop equations, first voltage equations are written for the bridge loops. By applying Kirchhoff's voltage law, the impedance ratio of one arm is equated with the impedance ratio of the another arm. So we obtain the relation I1 into R1 plus J omega L by I2 R2, which is expressed in terms of currents flowing through the resistance R3, resistance R and capacitor C. From junction current law, I3 equal to I4 plus IC. Dividing by capacitor current means I3 by IC equal to 1 plus I4 by IC. This helps to substitute unknown currents in the equation. From another loop equation, I4 R4 equal to IC into R minus J by omega C. Therefore, I4 by IC equal to R minus J by omega C divided by R4. Substituting this into earlier expression simplifies the equation. For bridge balance, real parts must be equal, imaginary parts must also be equal. After simplification, we obtain the final balance conditions. Inductance equation is L by C equal to R into R2 R3 plus R2 R3 R4 plus R into R2 R4 divided by R4. Resistance balance condition R1 by R2 equal to R3 by R4. The final inductance expression does not depend on frequency, which is a major advantage of the Anderson bridge. Hence, by adjusting bridge resistance until balance is achieved, the unknown inductance can be calculated accurately using the above balance equations. Now, let us discuss case bridge. which is another AC bridge used for the measurement of inductance. Case bridge is actually a modified form of Maxwell's Wien bridge. This bridge is mainly used when the phase angle of inductive impedance is large, or in simple terms, when the coil has a high Q factor. One limitation of Maxwell bridge is that it becomes less practical for high Q coils. To overcome this problem, case bridge is used. So, case bridge is suitable for measuring inductors having high Q values. A resistance R2 is connected in series with the standard capacitor C in one arm of the bridge. Because of this arrangement required, resistance value becomes small, circuit adjustment becomes practical, measurement accuracy improves for high Q injectors. Each arm of the bridge is represented using impedance Z1 equal to R1, Z2 equal to R2 minus J by omega C, Z3 equal to R3 plus J omega L, Z4 equal to R4. At balance condition, no current flows through the director. So the impedance ratio condition becomes Z1 by Z2 equal to Z3 by Z4, or Z1 Z4 equal to Z2 Z3. Substituting impedance value gives R1 R4 equal to R3 plus A omega L into R2 minus J by omega C. From this equation, inductance L and resistance of the coil can be calculated after separating real and imaginary parts. After multiplying the terms R1 R4 equal to R2 R3 plus L by C minus J R3 by omega C plus J omega L into R2. This expression contains both real terms and imaginary terms. For balanced bridge, real parts and imaginary parts must be equal. So equating the imaginary parts, omega L R2 equal to R3 by omega C. From this coil, resistance R3 is obtained. Equating real parts, R1 R4 equal to R2 R3 plus L by C. Substituting the previous result and simplifying gives the final expression for inductance L equal to C into R1 R4 by 1 plus omega square C square R2 square, and R3 equal to omega square C square R1 R2 R4 by 1 plus omega square C square R2 square. Hence, by adjusting bridge components until balance is achieved, both the inductance and resistance of a high Q coil can be accurately determined using case bridge. The advantages of case bridge is best suited for high Q inductors, requires smaller resistance values, provides accurate inductance measurement. Hence, case bridge is preferred over Maxwell bridge when measuring inductors with large phase angles or high quality factors. Now, next we discuss the Wayne's bridge, which is an important AC bridge mainly used for the measurement of frequency. Unlike Anderson and Hayes bridge that measures inductance, Wayne's bridge is used to determine unknown frequency of an AC signal. It is widely used in audio frequency measurement, harmonic distortion analysis, notch filters, and audio or high frequency oscillators. In this range, bridge consists of four arms. One arm contains resistance R1 in parallel with capacitor C. Another arm contains resistance R2 in series with capacitor CZ. The remaining two arms contains resistance R3 and R4. A detector is connected across the bridge diagonal, and AC supply is applied across the opposite diagonal. The bridge works on the null valence principle. At balance condition, the detector shows zero current. It means potentials at both junctions are equal. Therefore, Z1, Z4 equal to Z2, Z3, where each arm impedance is substituted using resistance and capacitive reactance. At balance condition, after simplifying the impedance equation, the balance relation becomes R4 by R3 equal to R2 by R1 plus C1 by C2. This represents the general bridge balance conditions. From the imaginary part of the balance equation, the frequency of the operation is obtained as f equal to 1 divided by 2 pi root of R1, R2, C1, C2. Thus, the unknown frequency depends only on load resistance and capacitance values. If R1 equal to R2 and C1 equal to C2, then the bridge becomes very simple and stable, which is why Wayne's bridge is commonly used in Wayne bridge oscillators. Wayne bridges is used for mainly frequency measurement, audio signal generation, oscillator circuits, harmonic distortion analysis. The advantages of this Wayne bridge is simple circuit design, high accuracy in audio frequency range, frequency independent of supply voltage, widely used in oscillator design. In this presentation, in this presentation, Unit 3, we conclude Maxwell bridge. It is useful in medium inductance measurement. Anderson bridge is, measures inductance accurately using a standard capacitor. In case bridge is suitable for inductors having high quality factor. Wayne's bridge is mainly used for PCS measurement and generation of frequency. Hence, AC bridges provide accurate electrical measurements based on the null balance method and eliminating errors caused by instrument loading. Thank you.